Okay, hello everybody. Uh, Thank you for this opportunity to present my work. This is a work joined with Enrique Saer. This work uh, concerns with a generalization of classical gauge theory to higher dimensional theory. Mm, uh, we know the classical instanton equation for a connection. We consider its curvature Fa, and a connection is said to be a instanton. It is solution to equation one. We know that solution of the equation one are also Yang-Mills equations. Uh, for dimensions greater than 4, we had a generalization to equation one by using a m minus 4 form, where n is the dimension of the manifold m. And we say that a connection is a sigma instanton. It is a solution of the equation 2. Of course, uh, uh, this is interesting in particular cases when appear particular n minus 4 forms. I am interested in particular for contact manifolds. Uh, but in general, solutions of this equation has torsion. That is, solution for equation 2 are not in general Yang-Mills connections. Mm. Examples from for this are, for example, in the classical sense for sigma equal 1 or minus 1. In the Kähler case, we can take this sigma and consider the equation 2 for solutions for this sigma. They are called Hermite-Einstein connections. Or in the case for a G2 manifold, we can consider the tree form, the J2 form to be sigma, and they are called G2 instantons. Spin 7 instanton by take sigma equal the 4 form preserved by the spin 7 group. A contact manifold that I am interested in this case is a manifold of dimension 2n plus 1. A contact structure is a existence of a contact form satisfying this condition, nowhere vanishing. Also, we had a Rip vector field satisfying this condition. The point is, when we had a contact structure, we had a splitting of the tangent bundle in a distribution called the contact distribution. That is a rank 2n distribution and a line triple line bundle. A Sasakian manifold, in particular, are contact manifolds satisfying this condition, or another equivalent definitions that you can see in Boyer and Galicki books. And the point is, for a contact structure, appear this natural form. In my case, for 7-dimensional manifold, Sasakian manifolds, I had sigma equal eta wedge d eta, where d eta for Sasakian manifolds, name called the omega, usually called omega, is a Kähler structure on the contact distribution edge. Okay. The equation 2 for this sigma, we can consider L sigma to be an operator from the two forms and consider its eigenvalues. This operator L sigma splits the space of two forms in these spaces. When this part here is are transversal forms in the sense that its contraction with the red vector are zero. And this here is the vertical component that with elements whose elements are formed with eta component. This split allowed me to call on, in some sense, of Z-dual and Z-dual forms. We call Z-dual contact instantons connection with curvature in this space, and anti-Z-dual instantons to be connection with curvature in this space. Also, we had these two definitions. I'm going to concentrate my attention in the case of Z-dual contact instanton, because if we consider a connection to be a anti-Z-dual contact instanton on a holomorphic Hermitian Sasakian holomorphic vector bundle on M, if we ask for A to be simultaneously compatible with the transverse holomorphic structure and unitary, so this forces to A to be flat. So I'm going to concentrate in this case. The motivation for this work is the following. In dimension 7, at least 3 different types of connections maybe appear. I have just called on G2 instanton and contact T instantons, but if I had a structure holomorphic structure, a transversely holomorphic vector bundle on the manifold, we can consider connections with being orthogonal to the Kähler form, and we curvature we 0 to par equals 0, and extend the usual notion of Hermitian-Jan-Mills connections. Also, the Chern connection definition extends naturally by taking omega to be the eta. So we had these 3 different type of instantons or connections, and I would like to study the relation of them. This is a result of the work of Enrique Saer and Calvo Andrade and Rodriguez. They get to characterize the G2 instantons in the case of M to be a transversally contact Calabi-Yau manifold, and they prove that the Chern connections are Hermitian-Jan-Mills, if and only if they are G2 instantons. With this paradigm, I get to prove the following.
Luis, can I ask you a question? Can you repeat again what you mean by a contact Calabi-Yau?
Okay. We had a Sasakian manifold with a transverse volume form. In special, especially we had a SON structure and a G2 structure in this case. So contact clavijados are Sasakian manifolds with SON structure.
Okay.
Okay. But in more general case for Sasakian, or just Sasakian manifolds, contact instantons. Okay, it should make sense to call on G2 instanton. So it's a contact Calavillao manifold. For a contact instanton is a G2 instanton. If we take chair connections, chair connection is G2 instanton is and only if is a contact instanton. So in particular, along chair connections, we add the three notions are equivalent. So I also came to define to do a John-Mills theory in this case. If I define a charge for connection A to be this expression, I can see that this charge depends only on the transverse curvature. This part is the set-dual part of the curvature, and this is the anti-set-dual part of the curvature. I had this inequality. In this here is the John-Mills functional. The important point here is that the charge defined on a variation of A, the charge differs by this term. If I consider a chair connection, this term in the equation 4 is 0. So for among chair connections, the charge is independent on the Hermitian structure, and we can denote it just by Ka, where A is the Sasakian holomorphic vector bundle. In this equality, we can see that, for example, if I had A to be a set-dual contact instanton, this equality, for instantons, for contact instanton, this part is 0 in both cases. If it is a set-dual, this part is 0. Is 0, so the John-Mills functional is equal to this charge. And this sign obstructs the existence of instantons in this case. Okay, so in the same way that the classical gauge theory for dimension 4, I would like to consider the modular space of instantons, set-dual contact instanton. So I can consider the deformation complex of an instanton and obtain the complex phi, where the first cohomology group models the formal tangent bundle. But the problem is that in this case, the complex phi is not elliptic. So a priori, I don't know if this local model is finite dimensional. In order to prove this, what I can say about this local model is summarized in this theorem. For a J bundle, I need to take N to be closed and connected Sasakian 7-manifold. In fact, the first cohomological group of the complex phi is finite dimensional, and it models the tangent space of the model space. But I can say more to this modular space. we can model this tangent space with a basic cohomological group in the sense that it's a cohomology of the basic complex or Fourier cohomology. And to obtain the dimension of the tangent bundle with this basic cohomology for this formula. Furthermore, if I consider irreducible contact instantons, the moduli space is cut out as the zero section of the obstruction map, and I can say more for the dimension of the moduli space. That is exactly the index of the certain transversally elliptic complex. Okay, I'm just going to give a sketch of this of the proof of this theorem. For details, I can refer you to my work in arXiv or my PhD thesis. The sketch of the proof is the following.
Sorry, one question. What's transversely elliptic?
Sorry?
What is transversely elliptic?
Okay. You need to consider the operators, the differential operators. In this case, restricted to forms transversal to the foliations generated by the Rip vector. Maybe I'm going to speak on this later. Can you answer your question on front?
Yeah, that's fair enough. Thank you.
Okay. Okay. The complex associated to the deformation complex, in fact, models the tangent bundle of the at that instanton, subdual contact instanton. But the problem here is that we don't know its dimension is finite. So to get this result, we identify the operator D7, that is the composition to the operator dA with the projection to this space. We identified with this operator, with this composition. With this, we obtain a extended complex. We can prove that this extended complex is in fact elliptic if I is a subdual contact instanton. So we obtain the finite dimensionality of the first cohomological group of the complex phi. In order to prove the item 2 and 3 of the theorem, we need to make another approach, because we can say few about the local model with we consider the extended complex. We consider now an ideal inside this grade Lie algebra, the ideal generated by this subspace. You can consider the ideal I generated by the another part, the anti-self-dual part, but no difference appear. The proofs are dissimilar, but I am interested in this case. Okay, the point is that if n is a k-contact manifold, it is to say that the rep vector is scaling. So this ideal is preserved by the operator dA. Hence, we can consider the quotient L valid, this quotient, and from this lemma, we obtain that the operator dA descends to the quotient for an operator D, because D square is the curvature of the instanton, so it's 0 in the quotient. We obtain a complex. And I can identify this space is L with sectional vector bundles. So I had a new complex model that, by definition, model the tangent space of the instanton, but in another approach. The thing is that the associated complex is LD is selective. So I had finite dimensionality of its cohomological groups. But again, I can say few of the modular space with the complex LD. But I can see that if I consider basic forms, that is forms transversal and satisfying this condition, I can find that the operator D restricts to basic forms in the complex, in the deformation complex. So I can restrict the operator D and I obtain a basic complex. And I can consider its cohomology. It's called Fourier cohomology. I'm going to denote by HB the cohomology of the complex H. The goal here now is to prove that the first cohomological group of the associated complex LD is isomorphic to the first cohomological group of this complex. Okay, in order to do this, I consider these operators. I recall that in presence of the affiliation, the space of K forms splits, in this case, like transversal forms and formed with eta component. So I consider the operation DB, whose kern is just basic forms, and the operator DT, that is just the horizontal part of the operator DA, of this operator. This is the horizontal part of this operator. We define the Laplacian of the operator D and the Laplacian and transversal Laplacian associated to the operator DT by this formula. We denote the kern of this operator and so-called the transversally harmonic forms by this space. And we obtain these isomorphisms between basic forms and transversally harmonic forms. This is the key of the proof, because I know I can consider the tangent space as a dual contact instanton to be harmonic one form, transversal harmonic one form, or basic forms.
Can I ask, is there a reason? Is there a priori reason for this term in the transversal Laplacian of dv squared? Is that just to make it sure that it's transverse, or is that something else? Yeah, exactly. is there an a priori reason that should be there, just so it's transverse, or is there another reason?
Sorry, I don't get your question.
So the question is this term. So you'd think that you'd think that it would just be the same as the Laplacian, just with this transversity that you've defined, but you get this other term. Is there the reason that that term is there to make sure that the outcome is like the image is transverse, or is there another reason for that? Is it just to obtain this isomorphism, or is there?
Because I don't know if that the reason really, because I had I need another model for my tangent space, because I get a relation between basic cohomology and the cohomology of the complex by a Giesing sequence. Okay. But I need this because it's easier to work with harmonic form, and in the case that considering, when you are considering, in some cases, this space coincides with the kern of this operator. You can forget the transverse part. Oh, this is the Giesing sequence. I can relate the cohomology with the basic cohomology, and the key to prove this, that this sequence is exactly the last isomorphisms. And if I compute, for some cases, I get a consequence of this. For example, the first cohomological group, this H1 is isomorphic to HB1. So I had a different model for my tangent space. So this space in the theorem, in the main theorem, is the obstruction to the modular space to be smooth, because the modular space is smooth when the obstruction mat is 0, and this is the obstruction to the obstruction mat to be 0. In order to prove this, I need to consider the Sobolev norms on the complex, for the complex LD. Just a notation, some notation. I denote by G the green operator of the Laplacian 4D. Delta is this composition. A plus are the Marie-Cartan elements. It is one form satisfying this condition. Here I'm considering the space of connections like affine space in the adjoint bundle. T epsilon is a slice at A inside the kernel of the formal adjoint D and with a small norm. And this symbol is to denote the intersection of the slide with Marie-Cartan elements. Variations of the Z-dual contact instantons remains Z-dual contact instantons if and only if alpha belongs to the Marie-Cartan element. We define the Kuranishi map by this formula, where delta is the composition of the formal adjoint of D with the green operator. And this map is invertible near 0 inside L1. We denote this neighborhood where this map is invertible by U epsilon. We define the structure map by this formula, taken by the harmonic part of the images by the inverse of the Kuranishi map. This is the bracket in the Lie algebra. And we can prove that for n is the Sobolev index greater than 3 inside of the neighborhood where the Kuranishi map is invertible. The inverse of the Kuranishi map maps the preimagine of 0 under the obstruction map diffeomorphically to a neighborhood W inside of the slice intersected with Marie Cartan elements. So, in the same way that the usual case for dimension 4, if we consider this gamma to be in this quotient, this space is a neighborhood of A inside of the moduli space. In particular, considering irreducible instantons, we obtain a local model for the moduli space of irreducible contact instantons. Furthermore, we can suppress the index because this inclusion is an homomorphism. This is the same result of Donaldson in the usual case. So for irreducible contacting instantons, we had a model of a smooth manifold when the obstruction map is 0. Of course, we don't know when this map is 0, but if it is, the moduli space is a smooth manifold. So, but this proposition say for us that a condition for this obstruction map to be 0 everywhere is the second cohomological group of the basic complex is 0. If we consider the basic complex, since the manifold is off-dimensional, and we define the transversal index to be the index of this complex, that index is 0, we obtain this formula, like a sum of the alternate thing of the cohomological groups. The index is computed, for example, if we consider irreducible contacting instantons, this term here is 0. And if we consider that this term is 0, this group is trivial, we obtain a formula for the index. It's exactly the dimension of the moduli space of irreducible contacting instantons. So we don't know when this is 0, or we are working on conditions for this cohomological group to be 0. But when it is 0, the moduli space has a nice local model through the charts given by the Kuranishi map, and we had a formula for this dimension, its dimension. Okay. Finally, if we had a moduli space, we would like to consider its geometry, or maybe define orientation for this moduli space. and we can define using the isomorphisms of transversely harmonic forms with basic forms. We can define inner product in the tangent space of the modular space at A plus alpha, where alpha is a one form. This is defined of this slide, but this does not depend of the slides. We can prove that we can consider just harmonic representatives for these guys. So we can redefine this inner product to be the same, taking harmonic representatives. So here is important the isomorphisms for elements in here being harmonic representatives. Now we would like to compute at 0 or to compute locally the last inner product. So we use the charts given by the Kuranishi map to compute this inner product and prove that this inner product to define a complex structure and prove that this is integrable, and so we obtain that the modular space has a Kähler structure for the Sasakian case. How this is made? This J, I want to recall that phi is the endomorphism of the tangent bundle of the manifold N. And in the Sasakian case, this phi restricted to the contact distribution is a complex structure. So if I consider these isomorphisms, we note that J preserves this space, and we can define a structure J induced by J in the tangent space of the modular space. We can also define a bilinear form given by this expression, where we take alpha and beta to be harmonic representatives, and it is a very long and straightforward computation in local coordinates using these technical results, because I need to compute the harmonic representatives of the imagine of a vector field inside the transversal harmonic forms pushed forward by the Kuranishi map, and compute this part. We obtain a expression for this guy, and with this we can prove that the inner product computed and these representatives, it has this expression, and the bilinear form omega has this expression here. So we could obtain that the almost complex structure J is in fact integrable, and this associated form is closed. So the modular space is a Kähler manifold. For Sasakian manifolds, we are working on currently on the case when n is a 3 Sasakian manifold. This is there exist 3 Sasakian structures satisfying some a sense of hyperkähler relations. So, but in this case, we cannot prove still that the modular space inherits a hyperkähler structure, but in the Sasakian case, it in fact is a Kähler manifold. So, but I just want to recall that all this is on the hypothesis that the modular space is a smooth manifold. For example, when the second cohomological group is 0, and we believe, and in fact is a conjecture in my work with Enrique, and we are working on it, that the positivity on the metric, on the contact metric, is enough to prove that the second cohomological group, basic cohomological group, is 0. So, for example, Sasaki-Einstein manifolds could be an example where we have this result is true. Okay, is done. Thank you.
Thank you very much for the talk.
Okay.
All right, are there any questions?
I have a question. Is there, other than this correspondence between G2 instantons and transverse Calabi-Yau, as in transverse Calabi-Yau instantons, is there a reason that in particular you can do this in 7 dimensions and not others? So, like, for example, there's this, I think there must be some transverse Calabi-Yau and correspondence with them, like the Sasakian instanton equation in 5 dimensions, say.
Yes, in 5 dimensions, there is a complete description to the modular space of contact instanton given by Baraglia and Hetmati. They describe the modular space, and some difference appear because when you are in 5 dimensions and you reduce 1 dimension for the horizontal distribution, essentially you are in the 4-dimensional case. And for example, the subdual contact instantons and anti-subdual contact instantons make sense to study the 2 cases. Here, we had, in some sense, we had a trivial case, and seven dimensions. Let me to tell one more thing on this of the motivation. That is, I believe that is very important.
Yeah, there's no need to rush at all. There is more time. You need to say something more for sure.
Okay. In 7 dimensions, we need to we would like to find examples of G2 instantons or contact instantons, or maybe transversely orbiting mills. And it's possible or it's interesting to find transversely emitting Jan mills using the Fourier Hitchin-Kobayashi correspondence. Jada, okay? Okay, thank you.
I have a question.
Sure.
Could you repeat the last last conjecture about the Sasakian Einstein matrix?
Okay. If we have the conjecture is that for a positive curvature for the metric, the second cohomological group is 0, so the model space is smooth. Sasaki Einstein are examples of metric with positive curvature. So this is an example, just an example.
And do you try that with homogeneous space using the because there are a lot of examples of 7-dimensional homogeneous space that are Sasaki Einstein. Even more, there are 3 Sasakian manifolds. So maybe there you have a lot of examples to try your conjecture.
Maybe we flag manifolds, but I don't try it. Don't.
Okay, thank you.
Okay.
Are there any more questions? All right. If that's the case, we finish here. Thank you very much for the talk, Luis. It was very interesting. Thanks for coming to speak to our event. And thanks everybody for coming. It was very nice to have you around, and hope to see all of you in future events, or if they're in the second installment of Olga later on in the year. Thank you very much for coming.
And thanks for organizing, both you and Daniel.
Yeah, thank you.
I thought it was very good.